Good afternoon. The presentation for today is on hypothesis testing, particularly in regard to errors of inference that can be made based on interpretations of null hypothesis significance tests, NHST. The schematic of null hypothesis significance testing that is used in the field shows on one side the experimenter's decision, which you should be familiar with from the tests that you have already learned. The experimenter''s decision based on obtained data can either be to reject the null hypothesis, top row on the left, or to retain the null hypothesis. And these are the data-based decisions. Those decisions are based on sample data that are intended to represent actual reality, an actual situation about which we can only hypothesize. But we posit that the actual situation exists. So we have two choices, two things that could be happening in the actual situation about which we are hypothesizing. One could be that the hypothesis is true. And on the table, that is the left-hand column. And in the case of, for instance, a comparison between a treatment, a treatment's impact on achievement and a control group's impact on achievement, that would be that treatment has no effect. The null hypothesis that there are no differences between the two means, treatment and control, is actually the case in the populations represented by the sample. The right hand shows the actual conclusion that there is a difference between the populations represented by the samples, and the null hypothesis is false. Now, if the null hypothesis is false, then it should be rejected by the experimenter. That is the event that happens in the upper right corner of the table shown. The effect exists, there's an actual difference at the population between the treatment and control groups, and the experimenter, recognizing statistically based on their statistics that there is a significant difference, rejects the null hypothesis. It's listed here as a correct decision. If there is no effect between the treatment group and the control group in actuality at the hypothesized population level, then what should happen if the researchers makes a correct conclusion is that the researcher should retain the null hypothesis because the null hypothesis is true. That is represented in the lower left corner of the table. There are two other conclusions that could be reached, both of which are errors. And those have names in statistics called type 1 error and type 2 error. So we're going to look at each in turn. So type 1 error is notated as alpha, and this is the same alpha that you have seen before. This is actually the definition of alpha that you have never really been introduced to in the past. And that is the type 1 error rate, is essentially the definition of alpha. And what it means is that in the actuality at the population level, and I'm going to keep the example of a treatment that and its effect on mathematical achievement compared to a control group, that there is no effect of that treatment, that the two groups have the same math scores, and that the null hypothesis is therefore true. Mu1 equals mu2, but the experimenter rejects the null hypothesis, concluding that there is an effect. That's called type 1 error. So the null hypothesis is true. The differences in the means of the samples are likely due to chance, but the experimenter concludes differently and rejects the null hypothesis, claiming that the differences between treatment and control are not likely due to chance. The other kind of error is called type 2 error, and it's represented by beta. Now, all of these Greek letters mean different things in statistics. They mean, each one of them, they means multiple things. So you'll see beta in other contexts. But in this context, and you'll also see alpha in other contexts, but in this context, beta is the type 2 error rate. And it pertains to the situation where there's actually an effect on math achievement of treatment. Mu1 does not equal mu2, but the experimenter, based on their data, fails to reject the null hypothesis. The null hypothesis should be, in essence, at the hypothetical level, rejected, but the experimenter's data doesn't represent that sufficiently well, and the experimenter retains the null hypothesis. So that's type 2 error. The experimenter does not reject the null hypothesis, but the null hypothesis is false. The differences between the means are not likely due to chance alone. So how do we maximize correct decisions in our analyses? Well, just like we had 2 types of error, we have 2 types of correct decisions. And one of them is in the left-hand column of the schematic, which is when the null hypothesis is true, when there actually is no difference between treatment and control at the hypothetical or actual, hypothesized actual population level. So the correct decision is what we want to maximize. So this actually has no name. It's the only one of these things. There's alpha is the type 1 error rate, beta is the type 2 error rate. We'll get to the upper right-hand quadrant in a minute, but the lower left-hand quadrant is just called 1 minus the type 1 error rate. And the numerical value is actually 1 minus whatever your alpha is. And your alpha is the same alpha that you have seen before. For instance, alpha equals 0.05. So 1 minus alpha is your probability of not finding statistical significance when there is no effect. That does not mean getting rid of those 2 knots. It's not the same thing. So we're going to think about that a minute. It's the problem of not making, the probability of not making a type 1 mistake. It's the probability of not claiming that there's an effect wrongly. And to give you just a minute's background on this, in experimentation, fairly strong conclusions are drawn when an experiment has very high claims about the validity of its conclusions for causation, particularly when there is random selection, random assignment to groups, control over extraneous circumstances. People make fairly strong conclusions, both about confirming psychological theories and about recommending practices. So it's very important to researchers that those conclusions that such and such is effective are not incorrect. So you really want to, particularly in the experimentation area, researchers really want to minimize the probability that they will commit a type 1 error. And so they want to set a low alpha. And since 1 minus alpha is the probability of not finding statistical significance when there is no effect, they want a high probability of that. They want a high likelihood of retaining the null hypothesis when it's the right hypothesis. Nobody really wants to retain their null hypothesis, but it's the safe thing to do, and it's the correct thing to do when it's true. So you don't want to make a mistake that kind of favors their possible publication rate. So how do you actually do this? And I guess the reason I go on about this for a minute is because it's kind of, in terms of, hey, I really want to reject my null hypothesis, it's kicking yourself in the foot. You make things harder for yourself. You use tougher tests. So for instance, if you set an alpha of 0.01 instead of 0.05, then that's your type 1 error rate. That means that you're going to try to make the correct decision 99% of the time. And with a 0.05, you're going to be okay with saying, I'm only going to ensure that I'm making the correct decision 95% of the time. I'm aware that there's this 5% of the distribution that could happen under the chance hypothesis, but I'm going to reject things out there, and I'm going to allow that. 0.01 says, I'm going to allow 1% to be, of those values at the tails, to be considered statistically significant, not due to chance. I'm going to accept that even values far from the body, but within the 0.05 range, nah, those aren't statistically significant. They might happen due to chance. So alpha of 0.05 means that you're going to accept as unlikely due to chance 5% of findings that might be chance alone. Alpha of 0.01 means that 1 minus alpha is 0.99, which means that you're only going to accept 1% of findings as not being due to chance alone. You're going to say 99% of values in the distribution might be due to chance alone. So similarly, the other conditions are that you can use to reduce your type 1 error rate are to run two-tailed tests instead of one-tailed tests, because the type 1, the 1 minus your type 1 error rate is higher. Your type 1 error rate is lower with a two-tailed test, because you may recall that with a two-tailed test, you're really testing both ends of the distribution at alpha over 2. So that's 0.975, whereas a one-tailed test is 0.95. And then there's a technique that we haven't covered in this class yet, but that is when you are running multiple tests, that you split your alpha over multiple tests rather than just allow a single alpha rate to pertain to each individual test. And we're not really going to go into that, except just note that if you split, for instance, if you're running 4 related tests, if they're related tests, the appropriate thing to do would be one of many techniques, the easiest of which would be to use, instead of alpha of 0.05 for each test, the conservative thing to do would be to divide that alpha of 0.05 among the 4 tests. So each test, for each test, you had a lower probability of a type 1 error. Typically in social science, particularly educational research, we accept a not highly stringent test unless we have very large sample sizes at an alpha level of 0.05, either one-tailed or two-tailed, which means that your probability of not committing a type 1 error is 0.95. It's kind of a acceptable type 1 error rate of 0.05. People generally in publications do not allow a higher alpha, which would be, so alpha of 0.1 would, for instance, mean that your probability of not committing a type 1 error was only 90%. So 10% of your findings might be false. And when you rejected the null hypothesis, it actually might just be happening due to chance. So we want to minimize that, but usually we do it within the range of alpha 0.05. Perhaps more interesting is what to do about maximizing correct decisions when the null hypothesis is false. So it's more interesting in non-experimental studies. So there's this kind of experimental studies want to be sure that their conclusions are not due to chance, and non-experimental studies often want to ensure that if there are statistically, or if there are real differences among groups, that you find them, because to neglect them would be not to paint a full picture of the circumstances at which you're looking at through data. So here, the decision correct rate, the correct decision rate actually has a name. And this is the case where of what they call power, which is 1 minus the type 2 error rate. And power is the probability of finding statistical significance when an effect is real, or rejecting the null hypothesis when the null hypothesis is false. Okay, so there actually is a difference between the treatment and control conditions in maths, or between the population that the treatment group represents and the population that the control group represents, between mu1 and mu0 or mu2. And there is that in reality at the population level, and the experimenter has the power to detect that difference and reject the null hypothesis. So we would like to reject the null hypothesis when the null hypothesis is false. So techniques to do that you can actually see in the formulas, how to decrease your type 2 error rate or increase power. And there are there are more than 3 ways, but there's 3 ways that really have to do with statistics. Many of the rest of them have to do with research design. So one thing is simply, well, overall, is to decrease the standard error term. So you may remember that in a statistical test like the t-test, the t-statistic is the difference between the means divided by the standard error of the mean. So one thing is you can have a low standard error. That would mean that your difference in the means proportional to the standard error was large. So you want to shrink that denominator term. So I've added in the t formula. This is the t formula for independent sample means, which is the one that fits with our treatment and control condition. And in the upper right-hand corner, you see that the T formula is the difference between two means divided by the standard error of the mean. So one thing is that if you decrease that standard error term in the denominator, then proportionally, whatever your difference between the means is will have a greater proportion, will outweigh the standard error term to a greater extent, and your T will be larger. So you want to decrease that denominator term. And so one way to decrease the denominator term is to decrease the denominator in the standard error term. I'm sorry, is to increase the denominator in the standard error term. There was a mistake there. So increase the denominator in the standard error term, which is n. So if you have larger sample sizes, your square root of n in the standard error term will be larger. Relative to that, s being constant, your standard error term will be smaller, and you will have an overall reduction in your standard error term, and your difference in means being equal, your T will be larger. In the numerator of the standard error term, you can also use more homogeneous groups. Now, sometimes you don't want to do that because it runs counter to your hypotheses. You want to be talking about a diverse group of people. But one of the reasons that a lot of psychological studies have been done on predominantly white middle class students in freshman psychology classes is that those people are convenient, but also that they're fairly homogeneous. And so they will have in their responses, relatively, there will be little variance in their responses compared to if there were a wider, more diverse pool of respondents. And therefore, the numerator of the standard error term will be small, which will make your overall standard error term small, which will increase your T statistic. And then it's perhaps obvious that a third way of increasing power is to increase the numerator of the T statistic. And that, again, really comes into research design, which is having a strong intervention. So if your math treatment condition is a powerfully impactful, intense treatment, then if it works, it's more likely to have a high contrast with the group that you're comparing it to, and then your numerator of your T will be large relative to your standard deviation, especially if you have low variance in the population sampled and a large N. And those three ways are the ways that you maximize power. So I think that this is a summary. There are more to be said about particularly power analysis and the type 1 error rate and ways to minimize type 1 error and minimize type 2 error, but they will be covered another time. This schematic certainly informs you of the basics, and I hope that this video has been helpful.